Welcome back, Marauders. In this video, we're going to be looking at finding the pH of a weak acid. And then once we do that, we'll be looking at percent dissociation of a weak acid. So first of all, a couple reminders that for a weak acid, Ka is very small. And that means that we make not very much of the product. We keep a lot of the reactants when it reaches equilibrium. So the things we're going to be doing here, it's an equilibrium problem. So we need to write an equation, an equilibrium expression, and then an ice table. So the problem here says calculate the pH of a 2.0 molar acetic acid solution. And so acetic acid is HC2H3O2. To simplify things, I usually just use the generic formula HA, where the A is your anion, so in this case, the acetate ion, plus H2O reaches an equilibrium with the acid donates its proton, so what will be left will be A minus, the conjugate base, and then it'll make H3O plus. You can write this out with or without the water. So I could have also written it out as HA reaches an equilibrium with A minus and H plus. Remember that hydronium and hydrogen are used basically interchangeably. They mean the same thing. So you can do it whatever way you prefer. We're going to make an ice table. It's going to be an ice problem because it deals with initial and equilibrium concentrations. So we'll make an ice table. And so you'll have one column for each of your reactants and each of your products. We can leave out the water. So if you wrote your equation like this with water in it, water is a liquid, its concentration doesn't change, so that can be left out. All right, so from our problem, let's see what we have. We're trying to calculate the pH of a 0.2 molar acetic acid solution. So the acetic acid is the acid, and its original concentration is 2.0 molar. And then these are going to be starting at 0. So your conjugate base and your hydrogen or hydronium ions start at 0 at the beginning. And our goal in this problem is we want to find the pH. What is pH? pH has to do with the concentration of hydronium or hydrogen ion. So we need to find this box right here. That's what we really need to find in order to be able to find the pH. Okay, so we'll write an equilibrium expression. So Ka is equal to, our products will go on top, so A minus and H3O plus will be on top. And then on the bottom, HA. So that's your equilibrium expression. We were given Ka in this problem. Ka was 1.8 times 10 to the negative 5. All right, so looking back at our ice table, what else do we have? Well, we don't have any of the equilibrium concentrations, so we're going to have to use a variable. We'll say that this goes up by x, so it ends up at x. This is a 1-to-1 ratio, so this will also change by x. It'll be x. And when these go up by x, the acid is going to have to decrease by x. So this will be 2 minus x. All right, so now we can plug these numbers into our equilibrium expression. So we'll have x times x over 2 minus x. Okay, and so we can solve this the way it is. We could multiply it out. It'll end up being a quadratic. One trick that you can use in this problem and most of these weak acid problems is that since Ka is a really, really small number, it means that not very much of it is going to move over here to the product side. Almost all of it's going to stay over here on the reactant side, which means that x is going to be a very, very small number. So when you have 2 and you subtract a really small number, it comes out to be pretty close to 2 still. So since this is still going to be pretty close to 2, I can make that assumption that this quantity is going to be pretty close to 2, and I'll just take the x out. Okay, we can only use that assumption when Ka is really, really small, meaning that not very much of it is going to go over here and become products. And so when we subtract a really small number from 2, it's still pretty close to 2, and that'll make our calculations a bit easier. You can try it without doing that. You can try doing the quadratic using your calculator, and you should see that you get a pretty similar answer to what I get using this method. All right, so I'll just use some simple algebra now to solve this. So I'll multiply both sides by 2, and I get 3.6 times 10 to the negative 5 is equal to x squared. And then I find that x is equal to 0.006. And so my assumption kind of makes sense that x is a pretty small number. And so 2 minus 0.006 is still pretty close to 2. So my assumption wasn't too bad. What does this x mean? Well, that means it's the concentration of hydrogen is 0.006 is your hydrogen, which is equal to H3O plus. Those mean the same thing. And that's what I really need in order to calculate pH. Remember that pH is negative log of hydrogen concentration. So our pH is equal to the negative log of 0.006. And we find that the pH is equal to 2.22. All right, so that's how to find the pH of weak acid when you're given Ka. It's an equilibrium problem, so you need to make an ice table, and then you'll use the ice table to find the equilibrium concentration of hydrogen ion, and then use that to calculate the pH. The second kind of question that you might see will be about percent dissociation. So what does percent dissociation mean? It means the amount that's actually dissociated, so the amount of the acid that becomes the product, the hydrogen ion and the conjugate base, versus what the initial concentration of the acid was. So if we look back here in our previous example, we see that our original acid was 2 molar, and in the end, only 0.006 molar for the hydrogen ion. So a very small amount of it dissociated compared to its original concentration. So let's do a couple calculations here. Calculate the percent dissociation of 0.2 molar acetic acid. Well, we just found out that in 0.2 molar acetic acid, only 0.006 molar is the final concentration of the hydrogen ion. So the amount that dissociates, 0.006 molar, over the original concentration, 2 molar, and then times 100. And so we find that we get about 0.3% dissociation. So a very small percentage of the reactant actually turns to products. Let's do that calculation one more time. This time we're going to do the percent dissociation of a 0.01 molar acetic acid solution. So we'll see that percent dissociation depends on the original concentration. So for this, we'll need to do another ice table to find the hydrogen concentration at equilibrium. So we have HA, our acid, reaching an equilibrium with the conjugate base and the hydrogen ion. We'll make an ice table. It's going to look just like the one we did on the last problem. The only difference is the initial concentration is quite a bit lower. So our initial concentration of the acid this time is only 0.01. These are both starting at 0. So these will increase by x, increase by x. This is going to decrease by x, 0.01 minus x. Just like we did before, we can assume that x is going to be pretty small because k is very small. So this is going to be pretty close to 0.01. And that'll make our algebra a little bit easier. It's not necessary that you do that, but it just makes the calculations a little bit easier. So our equilibrium expression, Ka, is equal to the conjugate base times the hydrogen concentration over the concentration of the acid. So 1.8 times 10 to the negative 5 is still your Ka value. It's still the same type of acid. The Ka values are going to be given to you in problems like this, or you can look them up in a table in the book. And then this will be x times x over, we're going to say that this equals about 0.01, since x is going to be very, very small. And so we solve this, and we find that x is equal to 4.2 times 10 to the negative 4. Okay, so 4.2 times 10 to the negative 4 is your final concentration of the hydrogen ion. And now we can calculate percent dissociation. So the amount that actually dissociated was 4.2 times 10 to the negative 4 out of the original concentration, 0.01, and then times 100, and we find that our percent dissociation is 4.2%. So one of the things we find here, looking at our 2% dissociations, is that in a weak acid, the percent dissociation is going to be increasing as the acid becomes more dilute. What does that mean? It means that at a low concentration, like 0.01 molar, a higher percentage of the acid is dissociating. And at a high concentration, like 2 molar, less of it is actually dissociating. This is still going to have a higher concentration of hydrogen ion, but it got that concentration with a lower percentage of it actually dissociating.